Everybody, in this video lesson, we're going to begin talking about the particle theory of light, looking at the energy of a photon. So let's get started. So our discussion on on the particle theory of light and how light was shown to be a particle as well as a wave begins with black body radiation. So a couple definitions to start, and then I have an applet to show you guys. So a black body is an object that completely absorbs all radiation falling upon it. And black body radiation is radiation that would be emitted by an ideal black body. So, all of us have experience with, if the sun is shining on something, it's going to warm it up. And maybe you'll notice, like, if you on a bright sunny day, if you leave all your windows open and the sun is on that side of your house and it just beats into your house, then the things in your house, they absorb that radiation from the sun and then emit it into your house, and it heats your house up. An ideal black body absorbs everything falling upon it and then radiates that back out as heat. And I think most of us have some understanding that, the more sunlight or something or radiation that an object absorbs, like the hotter it's going to get. We all have that experience, right? Like things is heating up because of radiation. So here's a graph showing for how hot something gets, what kinds of light you see radiating off of that. Now, I would like to show you an applet at this time. Here it is. And I have this linked on your handout. One of the links is actually, I just found out today as I was getting ready for this lesson, was actually broken, but the PhET simulation is up and running for sure. And so here we have this graph, and it shows you the intensity of different kinds of light for a certain temperature of object. So right now we can see we have this object for an object that's 5,650 kelvins, which is around the same Celsius. It's like off by about 300 or so. So for an object this hot, it's radiating all kinds of light, but the highest intensity you can see is in our visual spectrum. So blues, greens, yellows, reds, kind of almost all distributed evenly. And when you combine all those colors, when you combine all the colors of light, you get white light. And so this is why our sun appears for the most part white, because the highest intensity light being emitted from our sun is all in the visible spectrum. Now, when you get to stars that are a lot hotter, so maybe twice as hot, you can see that their curve is off the graph here. There you go. But see, their curve, the most intense light is now actually not even in the visible spectrum. It's past the violet. But the most intense as far as the visible spectrum is on the blue side. So you might see these stars as appearing kind of bluish. And then you can, as you go back down, and I'll zoom back in, as you go back down, you can see for stars that are hot, but not quite as hot as our sun, maybe like 3,000 degrees Celsius. You can see they have this orange or reddish hue to them. So if you take some astrophysics in university, you'll learn about all kinds of different stars, red dwarfs, et cetera, and a lot of them get their names because of their temperature and the kind of light that they emit. One last thing to show you, most of us have experience, cooking or looking at coals on a fire. But when you heat up an element on your stove, and it's just a piece of metal, it's usually kind of dark gray or black, right? But when you heat it up, what's the first color that it becomes? So as you heat it up, and you can look, if you look in the top left, you can see what kind of color that would look like, and you heat it up, you heat up, and you can see that it starts to glow a dim red, right? And then brighter red and brighter red. And then if you think about the light bulbs in your home, or think about if you've watched somebody work metal, like a blacksmith, the metal gets red, and then it gets orangey, and then it gets yellowy, and then it gets, what we have that expression, right? white hot, right? So you can see this as temperature goes up, you get to the reds, the orange, yellow, and white. And you see our like incandescent light bulbs at home. So this is incandescent. It's not like the new LED bulbs. But those light bulbs in our home give off that yellowy orange. They're not incandescent bulbs. Don't really give off that white light. It's more the yellowy orange light. But anyway, this is an interesting app. It just goes to show you how why things shine the way that they do. So heading back to our slideshow, you may be thinking like, what does this have to do with? Go away. Did I just actually close my PowerPoint? I actually just closed my PowerPoint. That's funny. Okay, back into the PowerPoint. So you might be wondering, what does this have to do with anything, with the particle theory of light? Well, it actually has to do with quite a bit. Because there was a problem with what theory said should happen with these black bodies and black body radiation, and what actually does happen. So we've shown the applet, and you can see what kind of shape the actual graphs have. So they, low intensity for like the infrared and longer wavelengths of light, and then it peaks kind of in the visible spectrum, but then it like shoots back down again, right? So keep that shape in mind. So what was the issue? The problem was, according to the wave theory of light, as the temperature of a black body increases, so should the frequency of radiated light. So what you should get, make sure I have my graphs. You should get something like this. So if we make a graph, and remember our wave equation, V equals F lambda, right? So that means that frequency is V over lambda. And if we're talking about light, that speed is C. So as the temperature increases, so should the frequency. But as frequency increases, it's proportional to the wavelength. So what you should have is, as lambda increases and frequency decreases, the intensity should decrease according to like a 1 over x curve, like that, because intensity is proportional to 1 over lambda. And that's not exactly true, actually. It's actually proportional to 1 over lambda to the power of 4. But you can see that relationship, right? Because the frequency, like UV radiation, very high energy, but with that high frequency, you have a small wavelength. And so if you converse it, if you have a high wavelength, low frequency, and the intensity goes down. So you can see that graph, it's going down, right? So that's what the theory said should happen. But did our graphs look like that? No, they did not. So this was a graph of intensity versus wavelength. What the observed spectrum was for intensity versus wavelength was something more like this. So we had a big hump like that. Now the graph looked pretty good, only to a point, right? The graph looked good. You had that kind of sloping down graph, but there was a region where it kind of broke down, right? It looks good for long wavelengths, and then as you get to short wavelengths, it kind of breaks down. If I can go to the previous slide, this one here. If you look at the one for our sun, for example, you got that nice inverse relationship, and then it goes up, and then there's a spike right here. And what region of light do you notice that this problem, where the theory and experimental match? They don't match for our sun. It's like right there. They don't match in that ultraviolet region. So we had a problem. So if light is a wave, and we actually have a lot of evidence, and in our last lesson with Young's double slit experiment, we actually proved, yeah, like light that has wave properties. It does diffraction, et cetera, et cetera. Light is a wave. But if light is a wave, how can we explain this? Because it doesn't. Light as a wave does not explain what's happening here. The region where the theory and experiments didn't match up, as I just mentioned, was the ultraviolet region of the spectrum. And they called this the ultraviolet catastrophe. and they couldn't explain this ultraviolet catastrophe with what they currently knew, that light was a wave. So we needed something more. As I mentioned, the problem was, as the temperature of a black body increases, so should the frequency of radiated light. But the point where that stopped being true was in the ultraviolet spectrum. Oh, that's just the same slide. I delete that one. All right, so how was it solved? So the German physicist Max Planck, and we'll see in a moment, he has his own constant named after him, was able to solve this UV catastrophe through a trick. And like at first, he was just like, I'm going to try this mathematical trick. He didn't actually know like what was actually going on behind the scenes. But the trick was saying that, an atom, and think of a black body absorbing radiation, the atoms warm up and started getting very excited, right? And so in theory, like the hotter something was, just the more energy and the more those atoms would vibrate. And in theory, if you have a temperature high enough, you can give those atoms a high enough energy, right? But Planck said that vibrating atoms and molecules couldn't just have any energy, but they were confined. So it wasn't just like infinite; they were confined to fixed levels. And what he predicted then, the spectra matched what we saw from that graph, the graph going up and coming back down, by saying that the atom could have certain energy levels, fix this problem. And the way it fixed this problem, and some of you guys probably already know this from chemistry, but an atom has different energy levels for its electrons. And those electrons, they have those like stable orbits, for lack of a better word, and they can't be anywhere else. They're always in these orbits. So when an atom gains energy, you have electrons that go to like a higher energy level. It's almost like increasing a potential energy. And they can like get higher and higher energy levels, but after a point, there's only so high that they can get. So they can't have infinite energy. There's like, it's very hard for them to get to those higher and higher levels. And what you have is that these atoms are absorbing photons and gaining energy levels. And when they drop back down, they emit a photon. And what he noticed was there was a connection between those atoms and their frequency and their energy and the energy of the photons coming off of them. And he said that the energy of these vibrating atoms was always a multiple of h, some constant, times the frequency. And this actually matches the energy of the photons being released. So I'll have a visual of that in a moment here. So we're going to talk about the photoelectric effect in our next lesson. Right now, we're kind of talking about Planck's work. But so he didn't exactly know that it was photons and the energy of the photons giving those vibrating different energy levels. But the later on, work by Bohr and the Bohr-Rutherford model of the atom offer an explanation of why the atom could only vibrate with certain energies. That's because we have these electron orbits, and when a photon is absorbed by the atom, it jumps up, and when that atom that was energized kind of drops down to a lower energy level, that energy is released as a photon. And that's why we weren't seeing the light emitted. And this is that emitted light that we were talking about in our black body radiation diagram. And the reason why we weren't getting a lot of emitted photons in this region here of high energy, it's because those atoms were never reaching that energy level. Those electrons were never reaching that energy level. And so they were never dropping down from that high energy level to emit light in this range. It was only in the visible spectra. And maybe this is the last thing I'll say on that. This is actually how we can deduce the composition of stars, because if we can observe the kind of light that stars are kind of emitting via this process, we can actually determine what kind of atoms they're made up of. And yeah, we don't get this ultraviolet light because those atoms in those stars, they're just simply not emitting like high enough energies. So electrons just don't get to that high level. The photon theory of light says that a photon is a discrete bundle of electromagnetic energy, and this discrete bundle is you can think of as being absorbed by, and this is just one type of way photons are produced, but atoms can absorb photons to jump up energy levels. They can emit them to drop down energy levels, and that emitted energy we can think of as a photon. It's a discrete bundle. It's a quantum of electromagnetic energy. When I transferred my note over to a PDF, looks like it got a little messed up there, but you can still read it. Photons are sometimes described as wave packets. If you take some quantum mechanics in university, after studying some calculus and statistics, you'll be able to mathematically represent these little wave packets. But for now, that's a bit way beyond the scope of this course. But what you need to know now is that these little wave packets we call a photon. They travel at the speed of light, and they carry discrete amounts of energy related to our frequency, as related to Planck's work. And this is kind of the grand finale of that. Get it right here. If I can find my cursor. Where is my cursor? There it is. Those discrete amounts of energy is this, the energy of a photon. This equation was up there earlier. It depends on its frequency. So if you have a high frequency photon, like ultraviolet light, X-rays, very high energy frequency, right? Very small wavelength, very high frequency, high energy. For light with low frequency and long wavelengths, like infrared, photons have less energy. But the energy of a photon is quantized. It's always this multiple of, it's always dependent on its frequency. So this is the big grand finale for this lesson. The whole buildup was to this, that photons have energy. You can think of them as a discrete bundle, a particle, quantum, if you will, that has a certain energy dependent on its frequency, E equals hf. And the best way, I think, to understand that this quantization of energy is to think of the Bohr-Rutherford-Malbay atom and just think of photons being absorbed and emitted. You have to have like fixed energy levels. So what are we going to do next? So now that we have our equation for the energy, so now that we've established that photons have energy, E equals hf according to their frequency, we're going to talk about the photoelectric effect. Because right now we have this photon theory of light, and it fits, and it helps with the math and resolve this ultraviolet catastrophe. But we didn't really have any evidence, experimental evidence, that this was true. So the photoelectric effect is kind of an experiment that proved that Planck was right, and then we can think of light as a particle having some energy. But that's for next time. So right now, you guys have a little bit of easy practice, just playing around with finding the energy of various photons. Just a quick note too, that an alternate version of V equals hf, since the wave equation, V equals f lambda, or in this case, c, since we're talking about light. The frequency is the speed of light divided by the wavelength. And so another version of this formula that you can use if you have the wavelength is that E equals h times c divided by lambda. So you might find that helpful just doing the practice problems. But yeah, those shouldn't take you too long, just kind of getting used to this idea, getting used to working with Planck's constant, which is another small constant. Where do we have it? 6.626 times 10 to the negative 34 joule seconds. So it's a very small constant. But yeah, just play around with that. And maybe one last thing. a lot of times and you guys should be used to this after our light unit, but a lot of times the wavelength of light, especially visible light, is on the order of a few hundred nanometers. So just to 1 nanometer, remember, is 10 to the minus 9 meters. So for example, if you are given that the wavelength of some color of light is, say, let's just say 500 nanometers, then if you want to get that to meters, you can just do 500 times 10 to the minus 9, and that will work perfectly for you. Okay, so just a couple of sides. The practice, I don't think you guys will find overly challenging. It's just getting used to this idea of photons have energy and finding that energy. But until our next lesson, guys, stay well, have a good day, and we'll see you soon.